right, so thanks everyone for coming to our colloquium. Today we're very happy to welcome Ian Moult to give our department colloquium. Ian was an undergraduate at UBC in the beautiful city of Vancouver, Canada, and got his PhD from MIT, where his thesis won the Sakurai Dissertation Award in Theoretical Particle Physics from the APS. He's now been an assistant professor at Yale for the past 5 years and is a winner of a Sloan Foundation Fellowship and DOE Early Career Award, amongst other awards. Professor Moult's research is focused on developing new methods for new techniques in quantum field theory for describing high-energy particle interactions in contexts ranging from dark matter to the LHC. And a common theme in his work is the use of effective field theory, which allows calculations relevant for the real world to be reduced to simple universal quantum field theory calculations. And today he'll be telling us about energy correlators at the collider frontier. So welcome, Ian.
Perfect. Yeah, so thank you very much for the kind introduction, as well as for the invitation. It's always a pleasure to visit Brown, and I've been having a lot of fun talking with everyone. So today what I'm going to be telling you about is a program that I've been working on for the last couple years now in trying to use certain ideas which come from more or slightly more formal quantum field theory, in particular something called energy flow operators or energy correlators, which I'll describe, to try and improve our understanding of the standard model of particle physics at real-world colliders, such as illustrated here. And so this has ended up being quite a long journey, but it's been extremely fun, at least for myself, because I've got to interact with people both from the more formal theory side, as well as with real experimental data and real experimentalists, to actually try and get some of these new ideas coming from the theory world really implemented in the current generation of experiments. And so what I want to do today is to kind of show some highlights from that journey, both on the more theory side and on the more experimental side, and to really kind of convince you of some of the exciting physics which is going on at the collider frontier on both the theory and experiment side. Okay, so let's get started. So as I said, the kind of big goal of this talk will be to try and understand these kind of complicated collisions which arise at very high energy particle colliders. And so in this particular collision, we have two protons which collided at 13 TeV at the Large Hadron Collider at CERN. And what we get out are these extremely complicated sprays of many, many particles which carry their energy off in very complicated patterns, and which are observed by experimentalists which are off in infinity. And so even though this looks extremely messy, and so you might wonder why people are interested in this, the reason why people in both theoretical and experimental high-energy physics are interested in trying to understand these collisions is that the detailed microscopic structure of the standard model, or of any beyond the standard model physics, is imprinted into macroscopic correlations, for example, as illustrated by these 3-point correlations here, in the energy flux which comes out into the detectors. And so if we want to learn about the detailed interactions of the standard model, or of any potential beyond the standard model physics, we really need to learn how to decode these patterns and translate them into the underlying microscopic physics. Which, as you can tell from these very complicated collisions, is a very hard task and places a huge difficulty on both theory and experiment. And so even though this is kind of a cartoon shown here, this is actually how we've learned much of what we know about the standard model over the last 50 years or so. And it's particularly fun to give this talk this month, because something you may or may not be aware of is this month actually marks the 50th anniversary of the discovery of what are referred to as jets. So this is just a technical name for these sprays of particles which are coming out in these pictures which I showed before. So the jets which were discovered 50 years ago were very small. So this is a picture of some of the early jets, which, as you can tell, are much, much smaller than these ones shown here. And in these early ones, so these jets had an energy of a few GeV. So it's essentially a factor of 1,000 smaller than what we see in modern particle physics experiments. But already this kind of started essentially a 50-year journey of trying to understand these kind of patterns in energy flux observed in colliders. And so already very early on, people were able to make kind of elementary measurements of these. And what I want to describe to you today is how this has really been turned into a kind of precision science 50 years later, where we'll really be able to kind of make precision measurements of the standard model using these patterns in energy flux which we observe in colliders. And so I mentioned this history both because I think it's quite interesting, And actually one thing as part of this project, which I'll describe, is we actually had to go back and use some very old data, so not quite 50 years old, but 35 years old, and we were able to resurrect this and really use this to help understand these modern colliders. And so this is something which I'll describe later on in this talk. But before going into these more details, I just want to take a step back and understand kind of how these particle colliders sit in the big scheme of kind of modern physics, and also what are the actual theories which are producing for us these very complicated sprays of particles which we observe in these colliders. So one of the most amazing things about our kind of current understanding of physics and our current theories of physics, which is gravity plus the standard model, which is the electroweak and strong forces, is that they're able to accurately describe our physical world over a huge range of scales. And so this goes all the way from kind of cosmology at the biggest scales to particle colliders, which I'll focus on here, which probe physics at the smallest length scales which we're able to access. And so, of course, the particular theory that or the particular scale which you're interested in will dictate which of these theories actually dominates the dynamics. And so if one is interested in very large scale physics, one is interested primarily, or one is dominated by the physics of gravity. At kind of modern or kind of R length scales, we're often interested in electricity and magnetism. And as we go to the smallest length scales of colliders, we're really interested in the microscopic structure of the standard model, namely the electroweak and strong forces. And so just from those names, one can probably guess that it's the strong force, also known as quantum chromodynamics, which really kind of dominates and is what produces these very complicated patterns which come out in these collisions. And so I'm not going to go through the details of the strong force, but the strong force, or QCD, is described by a Yang-Mills Lagrangian, which describes the interactions of quarks and the force carriers, which are called gluons. And so even though this has a very simple form for this Lagrangian, and it was also discovered approximately 50 years ago, it still is a kind of rich theory at the forefront of current research. And so there's two main reasons for this. So one is because it's what really describes almost all the physics of these hadron colliders. And so from a practical perspective, it's extremely important to be able to understand this theory. But the other reason is that it's an intrinsically extremely interesting theory which exhibits a variety of very complicated emergent behavior. And so part of what makes QCD so hard to understand is that its physics depends very strongly on the scale at which you look at it. And so famously, in the ultraviolet, QCD is really described by weakly interacting quarks and gluons. And so we can really think of it much in analogy with electromagnetism. But famously, in the infrared or at low energies, these quarks and gluons confine into the hadrons that make up the things in our everyday life. And so it's really this kind of interplay or this kind of change in physics as a function of the scale which gives rise to the complexity of QCD and also to these very complicated events which I've been showing you before. And so in particular, at colliders, what we produce are quarks and gluons at a high energy collider. At the microscopic level, we produce quarks and gluons. And these ultimately evolve as a function of scale into the hadrons which we observe in our detectors. And so this makes this theory extremely complicated to understand, and is why people have spent 50 years plus really trying to understand the details of this theory. And so to me, this is kind of a very beautiful problem because these particle colliders really provide one of the most spectacular examples of a very simple underlying theory producing remarkably complicated data sets. So from this very simple Lagrangian, we get out these amazing patterns of energy flux which we would like to understand. And this is very much in analogy with cosmology, where what we would like to be able to do is to infer the microscopic or early time physics of the standard model from these patterns in the asymptotic or late time energy flux. And because of the complexities of the theory of QCD, it is extremely hard to actually be able to do this, and so it's kind of hiding behind all the complexities of QCD. And so because of that, we really need to be able to develop very sophisticated techniques to be able to analyze and understand, both on the experimental end and on the theoretical end, how to extract or decode these patterns of energy flux. But before we get to these more complicated cases, we can actually go back to early cases where we could really just do this by eye and study kind of very simple patterns in energy flux. And this is actually how the gluon was originally discovered, and provides kind of a nice example of how these quarks and gluons manifest in long distance energy patterns. So if you collide an electron and a positron, and you draw the kind of lowest order Feynman diagram, what you get out are two quarks, which would go back to back in your detector. And so if you look at what you actually see, so here you don't need to use any kind of fancy pattern finding or anything. What you see is this very clear kind of pattern of these two jets, which I described, which are just these sprays of particles. And so here that you can really think about them, and it's very cleanly illustrated here, as proxies for these underlying quarks and gluons. And they're the kind of long-distance manifestation of the microscopic interaction. So here, if you just keep running these events, what you get is at some point, you'll actually have a microscopic interaction where a gluon is emitted off of here. And so what this gives rise to is this kind of three-jet, so-called three-jet event shown here, or kind of Mercedes-Benz configuration, where you have this one jet where you see the physics of the gluon kind of imprinted. And so at this level, it was very easy to do these analyses. You could really just run this many, many times. And there's this famous picture of this first three-jet event shown up here. And I think this was really like the 27th event. So you could really just kind of flip through. And one time you saw this particular event. But it kind of gives a really clean illustration of how you can kind of use these patterns in energy flux to learn something about the underlying microscopic dynamics of your theory. So as we fast forward to the LHC, these things are scaled up massively in scale. So instead of two jets, each with several GeV of energy, we now both get these massive events. So it's essentially the same picture which I showed you on the last slide, but scaled up by a factor of essentially 1,000. But in addition to these, we also get extremely complicated, not just three-jet events, but 4, 5, 6, essentially as many jets as you want. And so this is an illustration of a 9-jet event at the LHC, which is really testing the nonlinear interactions of quarks and gluons in this Yang-Mills theory. And so this really provides a spectacularly rich data set for understanding the physics of QCD. And it's really a kind of whole new playground where you can study QCD in these new energy regions and in much more complicated topologies. But it also places a huge challenge for theory, and in particular, even just being able to obtain a precise description of these very many jet processes has been a huge driver of theory developments in quantum field theory. And so this has really challenged theorists to try and understand the nature of the strong interactions much more precisely. But there's not just kind of more and more QCD as we go to higher and higher energies. So one of the very nice things about the Large Hadron Collider that makes it intrinsically more interesting than just a kind of scaled up version of these early colliders is it's actually the first collider where we have electroweak scale particles which can appear inside jets. So we don't just have kind of gluons which decay, but we can also have very massive particles. So for example, the top quark in the Standard Model or the Higgs boson, which are produced with sufficiently high energy such that they decay into a single jet. So we don't just have, for example, these nice quark and gluon jets, but we have jets with more complicated structures. So in particular, the top quark will decay into essentially a kind of 3 particles at leading order, which are really imprinted into these 3 pieces of energy flux, which you see here. So similarly for the Higgs, it decays primarily into, for example, 2 quarks, which are nicely imprinted into these 2 flows of energy, which are seen here. And so this really places jets at the kind of forefront because they become the long-distance manifestation of essentially all particles in the Standard Model. And so almost all the electroweak scale dynamics is really imprinted in the energy flow of these jets, and we really need to understand how to understand these patterns in energy flux if we want to understand a huge variety of physics at colliders. And so this idea of using these patterns in energy flux to understand the Standard Model is something which goes in the name of jet substructure. And so the idea of this is to really take advantage of these patterns in energy flux to provide new ways to study physics at the LHC. And so, of course, you can't actually observe the new particles which are produced at microscopic scales. And so you really need to do this by understanding these patterns in energy flux. And so this is kind of also fun to give this talk here because Jennifer and Matt are some of the real kind of heroes on the experimental side, which have really transformed this from just these nice little pictures which I draw to actual precise experimental measurements, which have really kind of revolutionized what one can do at particle and nuclear collider experiments and have really transformed the interaction between theory and experiment. So now there's really a huge variety of very precise new measurements on these energy flow, which have really enabled whole new sorts of measurements and have really revitalized the interaction between theory and experiment. And so there's a whole other talk which I could give on how important these new analysis and this jet substructure framework has been for searching for new particles or for characterizing particles in the standard model, such as the Higgs boson. But instead, what I want to do on this talk is to describe a little bit about how this has really influenced people in the theoretical world to rethink about questions about energy flux in quantum field theory. And so in particular, one of the biggest sociological impacts of this whole variety of new jet substructure measurements is it's really kind of reignited this very long, or this decades-long quest to achieve a precision description of energy flux in quantum chromodynamics, going back to these early pictures which I showed. And so much like when we study the CMB, we have these very nice measurements, for example, of two-point functions, which are done at remarkably high precision. We would like to be able to understand, can we do the same thing at hadron colliders? So can we have analogous, for example, measurements of two-particle correlation spectrum that we actually understand at the kind of percent level, where we can really do not just kind of qualitative questions, but we can actually extract kind of very precise physics from these very complicated events. And so these very inspiring experimental measurements have really motivated us on the theory side to go back and really kind of rethink this problem and understand what is the quantum field theory needed to do this, and how can we actually achieve a kind of similarly precise measurement or similarly precise theoretical understanding, just like we do for the CMB. And so we're, of course, not the first, as I mentioned before. And so the study of energy flux in QCD has a very long history, which is in some sense intertwined with the history of QCD itself. And so here I just want to go through some of these early understandings, because some of these ideas will be actually things that we will reinvigorate to be able to analyze these modern particle physics experiments. And so I should emphasize, so in particular for this history, which is now 50 years old, so I was not around during that period. And so any omissions or inconsistencies or errors in the history are not due to my purposeful slights, but are just due to the kind of people who I've learned this history from. Good. So right after the introduction of asymptotic freedom, which is also now just over 50 years ago, it became clear that you could start to try and compute certain short distance quantities perturbatively in QCD. So you actually now had a theory, this Lagrangian, which I showed before, where you could perform first principles calculations. And so one of the first calculations, which was performed in 1973, so this is actually before the discovery of jets, was of the total cross-section. So in other words, just this two-point function of two electromagnetic currents. And so these authors, so Appelquist and Georgi, computed this at the one-loop level in perturbation theory and showed that this was a kind of consistent theory. And this was a very important calculation, but in some sense, it's completely antithetical to what you actually want to do in colliders. So what they were computing was this kind of total cross-section to just produce anything, which is a probability. But what we really want to do, and what I've been showing you all along, is we want to understand how to image the states that propagate. So when you have these amazing detector displays, we're really kind of seeing the states which propagate inside this two-point function. And so we don't want just a number. We actually want to understand what is the structure of the states which propagate. And so this was brought to the forefront with the discovery of jets, because we would like to be able to understand how to ask, in theory, whether what you produce are just some uniformly distributed pions, or whether you produce these kind of collimated sprays called jets. And so we'd like to develop on the theory side an understanding of how to image the states that actually propagate in colliders. And so these authors famously kind of said in this original paper, can one say anything about this cross-section beyond the behavior of the cross-section? And they said in general, the answer is no. And so it's often bad to say that you can't do something. And so a few years later, there was a very important paper by George Sturman. And so he was motivated by what you actually do in a collider physics experiment. So in a collider physics experiment, you have all these kind of silicon, or you have some detectors off at infinity, which are making measurements. And so what he said was that I could introduce a single, or I could imagine kind of a very bad calorimeter, where I just have one particular idealized theoretical calorimeter cell, which measures the expectation value of the energy flux at some particular angle. And so he actually wrote down a kind of definition of such an operator would do this. It's in a bit outdated notation, and so in particular this eta is not the rapidity in colliders, it's actually the energy. But he wrote down a kind of idealized theoretical version of a calorimeter cell, and he said that what one could try and compute are the correlation function of, or the expectation value of this single calorimeter cell. And he showed that this was actually something which is calculable in perturbation theory in QCD, and so you get a finite answer if you did this. And so in his own words, at this point, the kind of energy flux became the focus of calculability. And so this was a very important step in kind of generalizing the study of energy flux from kind of like pointing in electromagnetism to the actual Yang-Mills theory. And so this kind of established the basis for how to think about these that all the kind of future calculations really built on. So just after that, this was kind of generalized by Stephen Ellis and collaborators, which said if I can do one, I can start trying to build up, for example, the full calorimeter that an actual experimentalist would study, and I can start putting more and more of these calorimeter cells. And so he introduced what are referred to as energy correlators, which are just correlation functions of multiple of these energy flow operators. So you can imagine just having like a calorimeter that just has two of these detector operators, and one can then study them as a function of the positions. And so this is exactly, of course, an analogy with what you do in the CMB for temperature fluctuations. It's just now that you're doing these for energy fluctuations. And so this is kind of his original kind of picture of this, where you can measure these as a function of the angle between the two detectors. And so he also argued that these would be something which was calculable from first principles within the theory of QCD. But the thing that which he actually did, which kind of went beyond what people had done before, is he actually performed the first perturbative calculation of this object. And so compared to what people do now, this is a very elementary calculation, but he was able to calculate it using these particular Feynman diagrams, and he computed the structure that you would actually see for the pattern of energy flux in your detector. And so from a modern perspective, this is very nice, because this answer really exhibits a kind of nice analytic structure directly at the level of the physical observable. So he really made a prediction that an experimentalist could go out and measure. And so even though these integrals are very kind of, or this is what is done in, for example, a quantum field theory textbook nowadays, at the time, the theory of QCD was very new. And so from talking to these, they were actually taught by Feynman how to do these particular integrals. And so I've talked a bunch to Stephen Wolfram, and because he has all his notes from that time, he actually has the original notes of Feynman teaching him how to do all these integrals. And for people that are more familiar with integrals, this is Feynman doing the kind of three-mass triangle integral, and he gets a very nice expression in terms of polylogs. And so he really taught, or Feynman taught, both Ellis and Wolfram and all these people how to actually do these integrals relevant for collider physics. And so now that one had a prediction for what this should be in QCD, you can go out and try and experimentally measure and test if this is actually what your underlying theory predicts. And so this was done by the Pluto collaboration. So this is a picture of this very old Pluto detector shown here. And so what they really went out and did was to measure this two-point correlation function of the energy flux, which is kind of illustrated here. And so remember, again, this is a function of the angle between the two detectors, so just like in the CMB. And so you have kind of two limits of this, one where the detectors are exactly 180 degrees apart over here, one where they're just kind of a generic angles like this, and then one where the detectors really become on top of each other, or what we refer to as collinear. And so they performed this very nice measurement at an energy of 13 GeV. So by today's standards, this is very low, so you're only producing a few particles. But nevertheless, they got out this nice distribution. And so now one could go ahead and actually compare this with these kind of first principles theory calculations of the strong nuclear force. And so when you do this, so this is actually a comparison between the calculations. So I mentioned this one by Ellis, shown here. And then this was combined with calculations by Parisi and collaborators, who specialized on this limit where the two detectors are nearly back-to-back, and by Veneziano and collaborators, who specialized on this limit where the two detectors come together. So there's actually quite a bit of theoretical firepower combined between all these theories here. But you can see that it agrees quite horribly with what you get out from the actual experiment. So it's qualitatively has some of the similar shape, but it's definitely not at the level of kind of a precision comparison like we have for the CMB. But nevertheless, essentially this initiated a very long road towards a precision description of the correlations in QCD energy flux. And so I'm not going to go through all of the history of the last 50 years, but I just want to kind of highlight a little bit how this kind of eventually died off. And so these are very important in establishing QCD as a theory of the strong interactions. So of course it was clear that things were qualitatively correct. And so people continued to do these measurements throughout the era of LEP. And so these are just two which I'm highlighting. So one is from the Mark II detector, where they increased the energy a little bit, now up to 29 GeV, and you can start seeing this much nicer, kind of smoother data from the better colliders. But you can still see that it's very far from the theory calculations showing here. And then I'll show the kind of final plot, which actually came out from the LEP. So this is a plot made in 2017 using kind of quite modern theory. And so you can see what is shown in these different lines is that you compute to higher and higher orders in perturbation theory. And so this is compared with the LEP data at much higher energies. And so you can see that the data gives this very nice, smooth pattern. But you can still see that even if you compute to what is still currently the state of the art at that time, things are clearly getting kind of better and better, but you never actually really make it to the data. And so this kind of precision understanding, or really understanding these at the really kind of like, let's say, percent level, proved extremely, extremely hard. And the interest essentially kind of faded starting in the early 90s. So people kind of forgot about these type of observables. And so in particular for myself, who kind of started off studying physics at the LHC, I'd never even heard of kind of this era of people studying these particular observables. And so this interest faded for a very long time, but it actually resurrected in a kind of unusual or unexpected place, which was in formal theory or string theory. And so in around 2008, Hoffman and Maldacena published this quite influential paper where they kind of resurrected this idea in the pure theory side. And so they wanted to kind of have a thought experiment about how you could have collider-like observables in certain conformal field theories, or just toy field theories that they could compute things in. And they abstracted these very complicated collider physics experiments to a very simple experiment, which is illustrated here. And so it's a bit hard to read, but this is made by David Simmons-Duffin, who works on the conformal bootstrap, where this has had a large impact. And so this is supposed to be a sample of the 2+1D icing model. And so what you want to imagine what you're doing in a collider physics experiment is you're essentially hitting this sample with some local operator. You're imagining you have some excitations which propagate off to infinity, and then you want to image these with some camera, which is some kind of detector. And so one thing which kind of came out of this, as you might expect, is that just like how in different theories you have different local operators, in different theories you also have different camera operators. So what is possible to measure will be different if I'm in QCD or if I'm in the icing model. And so there's been a lot of work in trying to understand how to formalize this kind of collider, so-called conformal collider physics setup for understanding the conformal bootstrap. And so one of the reasons why this is a little bit different than what you might be familiar with is that these camera operators are a little bit unusual in their form. So if you think about what you're really trying to do when you're measuring energy flux in a collider experiment and try and write down an operator that actually measures this energy flux, it turns out that these energy operators are kind of non-local in nature, or what are referred to as, in the modern literature, as light ray operators. So it won't matter in explicit detail, but it turns out that what they end up being is specific integrals, in this case of the stress tensor, if you want to measure the energy. And so the way that you think about what a kind of calorimeter cell is doing in the quantum field theory is that you want to take your stress tensor of your theory, which is the kind of measuring the energy. You want to dot it into some particular direction depending on the kind of the direction that you want to measure the energy flux in. You then imagine that your kind of detector runs for all time, so you're just imagining the flux kind of coming through your detector, and then you want to bring this off to infinity. And so this gives you a particular definition in quantum field theory of what a kind of camera operator actually is. And so these operators have been developed a lot recently in the conformal field theory literature, and there's now a very nice way of kind of manipulating them and understanding them in more general field theories. And so this is very nice because it really kind of connects these developments in conformal field theory with real-world jet substructure, and so we can try and use these developments as a way to improve our understanding of collider physics. But what we still really needed, so that's kind of nice off in theory world, what we still really needed is kind of an experimental signature or something we could really do with these, which we could not do before. And so one of the very nice things, which is kind of suggested by this way of thinking, which in some sense should have been obvious in hindsight, is to look for certain scaling properties which you often have in quantum field theory. And so in particular, Euclidean scaling is kind of a hallmark of quantum field theory, appearing, for example, in this total cross-section or in critical phenomena. And it's governed by the operator product expansion of local operators. So one thing which is really neat about this kind of way of thinking about these detector operators is that they also admit an operator product expansion. And so what that means is that as I take two of these energy flow detectors or two of these calorimeter cells, I can really think of them in the theory world as expanding them over some set of more general camera operators, just like I would for kind of local operators. But what this predicts is that if I'm at very high energies or in these collisions, even if they're very complicated, I should see certain scaling behavior in the angles as I bring these two detectors together. And so this provides kind of a universal prediction that says that as I study the kind of small angle limit or as I bring these detectors together, I should see some specific power laws which are governed by critical exponents of your theory. And so this is kind of a very nice result because it's something we can look for even in very complicated collisions. But if you go back and look at this kind of discussion, so this was proposed by Maldacena in about 2009, and this is kind of a transcript of his presentation at KATP. And he was questioned by David Gross and Polchinski, who kind of said, well, there's a huge amount of QCD data. Why don't people actually do this? So there's been all this data. And so this response was essentially that people haven't done this because they've never thought about doing this. And so this was kind of a very nice new idea for us. And so what we wanted to try and do was to kind of arm with this new theoretical techniques and this new way of thinking to really kind of translate this from this little toy picture of a camera and a hammer to kind of bring it back to the real world LHC and see if we could use this to enable actual precision calculations and new ways of analyzing data at the LHC. But the LHC is a little bit too hard, and so we wanted kind of an intermediate step to try and kind of test out these techniques. And so what we did was to try and use data from the LEP experiment, which is an electron-positron collider. And so the reason why we like this is an electron-positron collider is essentially a scaled-up version of this camera and a hammer situation. So in this electron-positron colliders, we really have a hammer, which is exactly the photon or the Z boson, which excites the QCD vacuum. And then our camera are these giant detectors, which were at the LEP experiment in the kind of 1990s. And so this is a very simple version of the full LHC, where we hoped we could kind of test out these new theory techniques. And so, of course, people probably know that the kind of legacy of LEP is known for extreme precision. And so in particular, it did these amazing precision measurements of electroweak physics at the Z pole. And it also performed some of the most precise data or most precise measurements of these energy correlators. And so we were kind of very excited that we could go back and actually try and use this data to compare with our new theory calculations. But when we did this, we immediately ran into a kind of problem that although we think of this data as being extremely precise from a modern perspective, or when we typically think of this data as being extremely precise, but when we actually look at it from a modern perspective, it's actually quite poor if we try and do things at the level that we would really like to now. And so just as a kind of illustration of this, you can kind of see the large differences or the large differences in the measurements in these different regions here, which are much, much, much larger than the experimental uncertainties. And also if you try and extract certain quantities, for example, the value of the strong coupling constant, I won't go through all the details, but you get very different values than the kind of world average. And so in particular, people have actually done statistical analyses of these data and have actually shown that they're inconsistent at the level that you would like for real kind of precision tests of QCD. And so this was a little bit unfortunate because, of course, LEP is no longer running. And so LEP has been retired, and if you go to CERN, you'll just find that you can go look at some panels, you can read about how nice LEP was, and you can go tour the old retired, in this case, Delphi detector. And so this was a little bit of a setback. And so what one wanted to understand, so one thing which these two experiments did, which was actually extremely nice, was that they invested a lot in data preservation. And so one thing which we wanted to do was, can we actually bring this data back to life? And so not just to kind of make some simple plots, but can you actually resurrect it to be able to do kind of precision or percent level physics in the modern era? And so this turned out to be a kind of very long project. And so this was initiated by this Yanji Li, shown here, in about 2017. And so he initiated a project to try and bring the LEP data into the modern era so that we could actually do kind of precision or percent level physics with it. And so this was possible thanks to the fact that these experiments actually still survive in some form at CERN. So if you go walk around, you'll find that there's actually this secretariat for Aleph, so it's a bit hard to read. It's shown in here. And so there's actually a few people which are still alive. And if you go into these offices, this is a Delphi event display, which is actually like stuck to the table, which is shown in the background. And it also kind of indicates the era where these event displays are just on transparencies instead of computers. And so there was kind of a long way to go from just finding these event displays to actually having nice data which you could analyze. And there was also a lot of kind of technical problems which one might not think of, which arose along the way. And so one of them was that this data is stored on very old, in this floppy disks, and so you actually need to run them on very old computers. And so even once one had found the computers that would actually be able to run this very old infrastructure, one of them in particular for this Aleph experiment was just password protected. And so you actually can't get back to the original the simulations for those detectors. And so this means you have to use some, so for one of the experiments we were able to get through, but for this one you can only use certain kind of very high level data coming from it. And so this is something they're still working on, but so there's been a lot of interesting technical challenges along the way. But after a lot of work, what has come out is that you actually now have these very nice data sets from both Aleph and the Delphi experiments, which you're able to analyze using kind of modern techniques. And so compared to modern experiments, another kind of interesting thing about these is that they're actually only 28 gigabytes. So you can really have them just on a very simple hard drive, and you can go through them in like several hours and really make a whole variety of new measurements. And so it's really kind of an exciting, a new data set which you can actually use. And so because of this, there's a large and rapidly growing experimental effort focused on analyzing this archival data, which now has members from many institutions to try and get the most out of this kind of resurrected data. But what I'll talk about in this talk is a particular measurement of using this for these energy-energy correlator experiment, or this energy-energy correlators, and trying to make precision measurements using this data. So one question which you should immediately have is that these correlator measurements are fundamentally limited by the detector resolution. So even if I can go back and get this data, how can we do better without having a new detector? And so in some sense, you can think of it as these cameras which we have are kind of very old, and we would like to be able to upgrade them to something better if we're going to actually get some new physics out. And so this is a little bit of a technical point, but I actually kind of want to highlight this because this is really what enabled us to do something actually new with this old set of data. And so one of the important points, so I'm not an experimentalist, but experimentalists will tell you, is that in these large experiments, or in these large kind of detectors here, you can both measure charged particles, which are referred to as tracks, which can be measured very precisely using kind of inner detectors, which you can think of as these very fancy cameras shown here. And so the difficulty, or the reason why that these experiments had poor resolution early on, is they were kind of really measuring all the particles which came out, including neutral particles, and because this was something which was told to them by the original theorists at the time. And so in particular, this comes from a kind of fundamental theorem in quantum field theory, which says that if you want to have something which is computable purely in perturbation theory, you really need to sum over all degenerate states, including both neutral and charged particles. And so the problem was that essentially the very nice high precision data was kind of locked in this inner tracker of these old experiments and had never really been analyzed to its full potential because it could not be compared with theoretical calculations. But since the LEP era, we've had huge advances in kind of modern effective field theory techniques, which really enable us to actually properly treat this issue. And so in particular, what one can do is one can do kind of an effective field theory type matching, which enables you to actually compute directly in terms of hadrons. And so we're able to actually perform, just like you do in a normal kind of effective field theory, essentially a matching between certain cameras which detect these hadrons and certain cameras which you can think of as kind of going in and actually measuring the internal quarks and gluons. And so by setting up this theoretical framework, it actually enables kind of precision theory calculations for measurements just with these tracking correlators, or just with these tracking detectors. And so this really enabled us to actually go back and look at essentially this whole data set, which had never been looked at before, of extremely high precision data measured on these trackers inside these Aleph detectors. And so this is essentially a kind of brand new, an amazing data set for studying precision QCD. And so just as one kind of fun connection, so a lot of these, or these pieces which are shown here, were actually measured at the LHC and are part of what it enables us to actually do this. And so there's a very nice and exciting synergy between the LHC and the LEP experiments. But now that we are armed with this, it's kind of nice to illustrate how much this actually improves our angular resolution, just like when we study the CMB. And so if you compare the angular resolution, which you got in these early Pluto experiments, compared to the kind of LEP experiments in the 1990s, with this kind of modern reanalysis using this internal tracking detector, you can see that we just get a kind of stunning resolution, which really emphasizes the amazing kind of power of these original detectors, even though they were never analyzed. And so we really get this kind of state-of-the-art image of QCD much, much, much beyond what we ever got at the time. And so now we can really use this to look at these energy correlator observables in a kind of completely fresh light. And so if you go ahead and do this, you can make this kind of amazing measurement of this two-point correlation function. So this is exactly what I showed before in this kind of very old data. But so now, remember, this is a function of this kind of angle between the two detectors, again, where they're back-to-back over here, and where they're kind of coming together over here. And you can see that where originally we had kind of several data points along here, here we really kind of have 100 data points, or hundreds of data points, with extremely, extremely small experimental uncertainties. And so this really kind of enabled, by looking at this old data set, the kind of most precise measurements ever of the correlations in QCD energy flux. And so once one has this on the theory side, this really motivated us once one has this on the experiment side, this really motivated us to kind of match this with equally good theoretical predictions. And so I won't be able to go through all the kind of technical details of this, but the way essentially we approach this is through a kind of divide and conquer approach, which targets specific regions with very high precision. And so we're able to calculate in particular about kind of these limits in this kind of small angle limit over here, and in this large angle limit over here with very, very high precision. And so what I'll show you is first just our theory calculations compared with the data in these two limits, and then I'll show you the full distribution which comes out. So first we'll focus on this back-to-back limit shown here. And so if one sees this, what one gets when one compares kind of very high loop calculations, so these are using certain 4 and 5 loop calculations, you actually get a spectacular agreement between these very precise theory calculations. So you can see it's now at the kind of percent or sub-percent level. And we get this kind of amazing agreement between these measurements of QCD energy flux and first principles theory calculations. So this is kind of very satisfying to see that by combining these modern measurements with our kind of modern state-of-the-art calculations, we could actually really achieve a kind of precision understanding of this energy flux in these collider experiments. In this other region, we have slightly less good calculations, so we can only do it at kind of 3 or 4 loops, but we still overall see very good at this kind of 5% or so level agreement between the theory and the data. And so again, we're really able to actually start to get things at the level of the kind of percent level comparison between theory and data. And so if we zoom out, essentially after 50 years of kind of working on this problem, both with renewed experimental effort as well as renewed theory effort, we're really kind of for the first time actually able to bring this under real precision control. And so as we go from the 80s to the kind of 2017s to the 2025s, we're really for the first time, by using these kind of modern theory techniques, able to actually achieve a kind of percent level description of these QCD energy flux. And so this more generally provides a very exciting program of precision QCD measurements using all this resurrected LEP data. But that's not what I'm going to talk about here. Instead, what I want to do here is really push on towards actually using this to understand our original goal, which was these very complicated collisions at the LHC. And so this is really trying to use these for a quest for precision jet substructure at the Large Hadron Collider, which, as I mentioned before, is something I've been working on for a long time with my collaborator, Wajing. And so the complexity of these hadronic final states at the LHC, which we started this colloquium with, has really presented an enormous challenge to achieving precision jet substructure. So as compared to the case of these LEP experiments, we really get these extremely complicated collisions with kind of gluons and quarks flying everywhere, and these extremely huge detectors to see them. And so what we wanted to understand is, can we really overcome this by targeting this very simple universal scaling, which I mentioned, which came out of trying to understand these detector operators. And essentially, can we move this from the case of E plus E minus to this very complicated environment? And so the first thing one did was to go out and see if one could actually measure this. So if you can't measure it, then you can't even try and begin to compute it. And so this is something which is actually measured by a whole variety of experiments. And so what is being measured here is exactly what I showed you before, but now one is measuring this 2-point correlation function just inside these very high energy jets at the LHC. And so as I said before, what we expected was to see this nice scaling law, which was predicted in the formal theory world. And remarkably, what you see is a beautiful kind of power law once you're inside very high energy jets, so getting close to 2 TeV, and you really see this beautiful scaling over multiple orders of magnitude. And so this really showed that you actually see the scaling prediction that was originally predicted in theory. And so now what we'd like to do is to try and understand this quantitatively, and to really have theoretical calculations which are able to describe this. But it's also interesting just to compare this to the original measurements. And it's important when doing that, so it's to emphasize the angular scale of these measurements. And so in particular, if you see here, this is really measuring out to angles at the outer here of a 10 to the minus 1. So this entire plot, which is shown here, is really inside essentially this first data point in these original measurements shown here. And so this is really showing the kind of power of these very high energy colliders for making precision QCD measurements. And this has really kind of transformed, as I mentioned earlier, the interaction between theory and experiment. And if you look at the citations to this original paper on the energy correlators from the 70s, there's been this massive spike recently, and this is really due to the availability of this data at these large colliders, where we can start to try and really test QCD in this nice new regime. But of course, this presents a very difficult challenge to trying to make precision calculations which actually describe this in these colliders. And so the reason why these colliders are so difficult is to be able to even start to describe these very complicated interactions of quarks and gluons, as opposed to the very simple case of electron-positron colliders, where this was able to be done with kind of pen and paper by Feynman. You really need extremely complicated scattering amplitudes to even start initiating the progress. And so this is something which has really been made possible by tremendous efforts over the past several decades, both by Zvi Byrne, Lance Dixon, and David Kossauer early on for tree amplitudes, and the mathematics of these very complicated integrals which are really required to do this at the percent level has really been pushed by Anastasia and Marcus, and so this has really enabled it to be possible to even start to be able to ask these questions. And so these very complicated integrals are really used as a kind of basis for all the calculations which these energy correlators are based at the Large Hadron Collider. And so what you can do is you can stick in these state-of-the-art amplitudes, and you can go to make a measurement of this energy correlation function as a function of the angles, and you can try and integrate these amplitudes over the complicated phase space of the LHC. And if you spend about $1 million, you'll get the following plot shown here. And so the problem with this, so this is an amazing illustration that it's even possible to use these very complicated amplitudes, and it's a very nice interplay of theory ingredients and experimental ingredients. But the problem is that all the physics, at least that one wants for this scaling, is really inside this final bin shown here. And so if we really want to be able to actually study this with very, very good precision, we really need to kind of go beyond this unless we have kind of unlimited money to be able to spend. And so this is where these kind of new techniques, which emerged out of this more formal theory, really enabled us to be able to perform these calculations. And so again, I won't be able to go through how this is actually done, but essentially what one is able to do using these modern effective field theory techniques is essentially combine the ideas of these detector operators coming from conformal field theory using some complicated matching procedure with these underlying scattering amplitudes and actually kind of produce out real physics in this very complicated environment, which actually achieves kind of percent level precision for these correlation functions at the Large Hadron Collider. And so if we go and do this, and so this is a project that actually started with these 3 students when they were undergrads, and so they're now all postdocs. And so this took a very long time to actually bring it to reality. But we were able to actually achieve kind of very precise calculations for this scaling behavior in real world, which can be compared with these measurements by CMS. And so these are all computed at very high perturbative orders. And so you can see a kind of beautiful agreement of the scaling behavior. It's a bit hard to see the difference between theory and experiment because they're so close. But you can really kind of see at a quantitative level this scaling behavior. And because it's so precise, you can actually use this to measure the value of the strong coupling constant, which actually dictates the slope in the real-world LHC environment. And so this currently provides the kind of most precise extraction of the value of the strong coupling constant from jet substructure. And we're very optimistic that using these kind of high energies and amazing colliders, one can really take this further and actually get kind of the world's most precise measurements of these quantities. And so this is very exciting for us that we were able to actually kind of break this long-standing barrier and start to achieve a precision description of energy flux at the Large Hadron Collider. And so this is now kind of 50 years of experimental efforts. And so we've really gone from this kind of original plot where we've kind of transformed this into a kind of precision field where we can use both this archival data and modern LHC experiments to really understand this at the kind of percent level. So we've really kind of transformed our understanding here of these different kinematic limits to really be able to do this at a quantitative level and to extract quantitative predictions about the strong nuclear force. And so for us, this is really not the kind of end, but it's just the beginning. So now that once you can do this, you can start to use it to ask a whole variety of very interesting questions and really start to explore kind of physics beyond this absolute simplest case. So it's possible not just to measure these 2-point correlation functions, but just like in the cosmic microwave background, you can also measure non-Gaussianities, which is now being illustrated by CMS. And you can start to use this to probe more exotic states. So for example, top quarks or the Quark Gluon Plasma. And you can now really start to kind of unlock the kind of precision potential of all this exciting physics, which is hidden in this energy flux. So this is very exciting for us that we're now able to do this. Okay, and so just to conclude, so hopefully I've convinced you that colliders really allow us to access a wealth of very exciting phenomena, ranging from kind of precision QCD to ways of studying the Higgs boson. And in the last maybe 5 years or so, there's really been a huge revival and significant progress in trying to understand the description of energy flux in collider physics experiments. And so this is a very old problem, but it's being kind of resurrected with some nice insights from formal theory, which we've really kind of pushed through to enable predictions in the real world, at real-world colliders. And so 50 years after their introduction, these very simple energy correlator observables continue to drive a kind of very vibrant interaction between theorists and experimentalists, exploring the standard model, and hopefully there'll be many more years of this to come. Thank you.
Oh, thank you very much, Ian, for that beautiful talk. Let me turn on the lights. And we should take some time for questions. Sure, go for it, Chungi.
In one of the slides, you plot the ratio of 4 points of the 3 photons.
Yeah.
There's an index gamma 4 minus gamma 2.
Yes. Yes.
Is that calculated by the Bernoulli theory? Or
Exactly. Yeah. So I didn't explain it exactly. So when you study these, so I mentioned that there's this operator product expansion where you can take two of these detectors, and if you bring them together, you can essentially expand this over some more general detector, and each of these has a particular anomalous dimension. And so what is actually measured experimentally is a particular ratio of this 3-point correlation function over the 2-point correlation function. And so you can imagine this as having just some shape of the 3.1 and seeing how it scales with energy, or how it scales as a function of the angle, and divide that by how the 2.1. And so each of these has a different anomalous exponent, so these happen to be since you'll know that the kind of twist 2 spin j anomalous dimensions. And so this gamma 4 is associated with this particular operator for the 3 of these detectors, whereas this gamma 3 is associated with this one. And so these are known to each to so they're actually known to 4 loops, but what we can use them to is 3 loops. And so what these are kind of illustrating up here are some of the Feynman diagrams which are used to compute these as a function of the strong coupling constant. And so these are kind of encoded in this intermediate step here, which really makes sure we properly describe this scaling behavior at very high perturbative orders. And so that's really what enables us to actually get the precision values of the strong coupling constant out. They're small, but so they're small particularly at these very high energies at the LHC. But so you can see that in this particular scaling, which is shown here, so if there were no quantum corrections, this would be exactly flat. And so this is really just a probe exactly of the quantum corrections. And so they're small, but they're observable.
I hear chattering in the hallway, so maybe time for another quick question.
Thanks, Ian. That's a very nice talk. I was wondering if you looked at the jets with very few particles, like tau jets, hadronic jets, where everything can be described by a 3-point function, more or less.
Yeah.
Can you discern something about this? Say, find a better way of reducing QCD background, or just learn about tau decay and polarization from first principles?
Good. So that's a good question. So I think the place where these have the most strength is when you really have kind of many particles in your final state. And so when you have a relative, like if you really just have a 3-body decay where you can identify those particles, then just by kind of studying the angles and the kinematics of that is almost no different than studying these. Because if you really it's almost like weighting them by their energy. And then it's essentially the same as studying the actual exclusive decay. And so where these really gain is when you have kind of many particles and you just want to ask a kind of statistical question. And so this is the motivation for them actually in conformal field theory is if you just have some kind of mush of things coming out, you just kind of want to ask statistical questions or correlations about this. And so they really work most nicely for asking questions in this kind of very many particle limit. And they kind of lose in some sense their power, or it just reduces to studying amplitudes if you reduce to kind of few particle kinematics.
Okay, then let's thank Ian again for the nice talk.